Okay, welcome everyone to today's IvS seminar. Today we have Peter, who's going to be presenting his work as a postdoc in Denise Group. Peter did his master's degree at the Université Paul Sabatier and then completed his PhD at the University of the Côte d'Azur and now is a postdoc in Denise Group. So hopefully we'll hear all about his work today. Thank you, Peter.
Okay, thank you for the introduction and thank you everyone for being here this morning. So I've been here for about 6 months now, and one of the weekly highlights has been the cartoon that features in the newsletter. So I thought I'd begin with one that I suppose is relevant for today's topic. So we all know that the university this year celebrates an anniversary, but it is also a milestone year for the field of exoplanetary science, because this year is the 30th anniversary of the discovery of 51 Pegasi b, and this is the planet that revolutionized the field of exoplanetary science. So the plot on the left shows you the optical motion of the star that was induced by the presence of 51 Pegasi b. And these measurements were taken with a method known as radial velocity. Now, although a few planets were detected prior to 51 Pegasi b, it was the first confirmation of a planet orbiting a Sun-like star. And this is why the discovery subsequently led to the Nobel Prize. Now, before the discovery of exoplanets, the general consensus was that smaller planets would orbit closer to the star, and perhaps the more massive ones would remain further out. But the 5,000 plus exoplanets discovered so far are not like our solar system planets in terms of planetary positioning, which is evident in the plot shown here of the exoplanet population and the comparison with the solar system planets. What you can also see is that the majority of the planets have been detected with indirect methods, such as radial velocity, transit, and microlensing. Indirect methods infer the presence of a planet by measuring stellar perturbations, whereas direct imaging captures the photons from the planet itself, which perhaps could provide the best means of finding life elsewhere in the universe. However, few planets have been directly imaged because it is extremely challenging. So we can examine this challenging nature with the planetary system shown here. A high angular resolution is needed to distinguish objects separated by a few astronomical units and located tens of parsecs away. A high dynamic imaging capability is needed to overcome the large contrast between a faint planet and its bright host star. And this contrast ratio varies if the light captured is emitted or reflected by the planet. So the conventional approach to addressing this direct imaging challenge has been the use of a single aperture coronagraph with an adaptive optic system on a large telescope. A coronagraph is a focal plane mask that blocks the starlight so that we can observe the planet. An adaptive optic system uses a deformable mirror to correct for atmospheric phase perturbations in the incoming light. But the angular resolution of a telescope is limited by diffraction, whose characteristic scale is given by the ratio lambda over d. And this is why the majority of the directly imaged planets have been detected on wide orbital separations. Here I show you an example of the exoplanet HIP 65426b, which was detected at the separation of approximately 20 lambda over d. And this planet was first imaged with a ground-based instrument sphere on the Very Large Telescope. Recently, the James Webb Space Telescope imaged the same planet, which is shown here on the right. And what we can see in both images is that the planet has been detected at different infrared wavebands. At infrared wavelengths, the planets are more luminous, and the star has less flux, which provides an advantageous contrast ratio. So to gain high angular resolution, we can resort to long baseline interferometry. An interferometer is an array of 2 or more apertures that work as a single telescope to provide higher resolution images. And the angular resolution is now given by the ratio lambda over b. And mature infrastructure for long baseline interferometry include the CHARA array in California and the VLTI in Chile. And the long baselines provided by these observing facilities will enable the direct imaging of exoplanets at separations less than 10 AU, where radio velocity and transit methods are more sensitive. So you might be wondering how we block the starlight with multiple telescopes. For this, we use an observing technique called Nulling, which was introduced in the 70s by the Australian astronomer Ronald Bracewell. Bracewell's method or concept was later elaborated in the 90s, and this led to the NASA TPF and ESA Darwin missions of a space-based Nulling interferometer for exoplanetary science. But due to technical challenges and the limited scientific study of the exoplanet population at the time, these missions did not proceed. But since then, however, our knowledge of exoplanets has increased, and vast progress has been made in several key technologies. And this has led to the on-sky implementation of the Bracewell Nulling interferometer on several ground-based telescopes, such as the Subaru, Hale, and Large Binocular Telescopes, which respectively host Glint, PFN, and LBTI Bracewell nullers. It is important to note that Glint and PFN implement Bracewell nulling across pairs of subapertures located within the telescope. LBTI uses 2 apertures that are installed on a common mount. But the principle of Bracewell nulling is the same for all of them and can be explained with this schematic shown here. So light from a star is incident on 2 apertures separated by a baseline, by distance b, the baseline, and coupled into a recombiner made up of beam splitter depicted here as M. A beam splitter combines the signals from each input to produce 2 outputs. 2 in-phase signals combine to produce a bright output where the on-axis light of the star is directed. For the second output, a pi phase shift is added to the signal of one input. This means that when the light is recombined, one input is out of phase from the other, and so destructive interference occurs, leaving no starlight. And given a suitable baseline, the off-axis signal of a planetary companion will reinforce in this so-called node output. Now, the figure of interest in Nulling interferometry is the node depth, and this is the intensity ratio of a node output over the bright output. The lower the node depth, the fainter the companion you can detect. Now, the the performance of a nuller is dominated by atmospheric and instrumental phase perturbations, which means that at 100 nanometer phase perturbations, you get null depth distributions which look like this, and one would have to use methods such as numerical self-calibration to deduce the null depth. Numerical self-calibration is a statistical approach to modeling all the error terms, and is fairly complex to implement. And this is what motivated the advanced nulling architecture that I will focus on today, which is called kernel nulling. So this is the outline of my talk today. I'll just leave this on for a few seconds, then I'll proceed, I suppose. So, so what is kernel nulling? So kernel nulling is follows the Bracewell concept, and it is a nulling architecture and data reduction technique that uses 3 or more apertures. Although it's important to note that although an increased number of apertures adds complexity to the system, it does enable a greater suppression of the on-axis source. Kernel nuller theory was introduced in this 2018 publication by Martin Ash and Ireland, where they proposed a 4-input, 7-output kernel nuller for the VLTI. So here I show you a schematic representation of this kernel nuller. I have used complex matrix plots to depict the input phase combinations at each output. And in these plots, the input phase is represented by colored arrows whose length encodes the amplitude. So in the first stage, 4 in-phase signals from the VLTI unit telescopes interfere constructively to produce a bright output. For the 3 dark outputs, 2 out of the 4 inputs are pi phase shifted, similar to the Bracewell nuller you have seen previously. But in order to build these self-calibrating observables, which we refer to as kernel nulls, you need to further break down each of these 3 dark outputs into 2 non-symmetric outputs. And you do this by adding a pi/2 phase shift to the dark outputs. And from the resulting complex matrix plots, from the complex matrix plots of the resulting 6 row outputs, we can see that pairs of outputs are mirror images of each other. And this is an attribute that enables them to form a kernel null that is independent of phase error induced by the atmosphere or optics. And for this 4x7 kernel nuller, we can obtain 3 kernel nulls. So a direct way of interpreting the effect of a nuller recombining more than 2 apertures is to compute transmission maps, which describe the response of the different outputs to the presence of a test point source over the interferometric field of view. What this simply means is that if an exoplanet was located in a bright region of these maps, we would be able to detect its signal. If it was located in a dark region, we won't be able to detect it. So here I show you the 2D transmission maps of for the 3 dark outputs of the first stage over plus minus 15 milliarc-second field of view, both in right ascension and declination. The transmission here is expressed in units of flux collected by a single aperture. These classical nuller transmission maps are symmetric about the origin. On axis, the transmission is 0, where the host star would be located. But in these raw nuller transmission maps, we can observe an asymmetry, which provides a stronger constraint on the position of the planet. And another benefit of this asymmetry is that it allows for the elimination of centrosymmetric astrophysical features that would otherwise hide the signal of a planetary companion. The kernel output maps that are linear combinations of asymmetric transmission maps are also asymmetric, whereas raw outputs are a measure of flux. Kernel outputs, which is always positive. Kernel outputs can take negative values, as shown by the color bar here on the right of these maps. Martin Island computed these maps for a snapshot scenario at zenith that did not attempt to account for the Earth's rotation and its impact on the observable quantities. During my time in Nice, I developed a Python simulation that takes into account the Earth's rotation, which affects such maps, but also improves the detectability of exoplanets. So the plot on the left shows you a UV coverage plot. UV coverage plots are used in conventional optical interferometry to describe the richness of an astrophysical scene. Baselines formed by pairs of VLTI unit telescopes sample the complex visibility function at spatial frequencies labeled with coordinates u and v. The simulation I developed applies the same coordinate transformation matrix used for UV plots, but modified to only take into account baseline projection effects. And this results in the projected geometry of the interferometric array relative to one subaperture arbitrarily chosen as the reference. So with the east and north coordinates of the UTs over a plus minus 4 hour range of hour angle, we can compute the raw nuller transmission maps with time, which are shown here in the red block. So the six outputs are identified here on the left, and the 9 pointings over the plus minus 4 hour range of hour angle are shown here at the top. And in the first column, we can observe that the transmission patterns have a broad appearance when the projected baselines are short, and appear narrow when the baselines are long at zenith. And as the source moves away from zenith, the baselines begin to shorten again, and we notice a progressive increase in the size of the transmission patterns. From the time averaged transmission maps, which are shown here in the pink block, we can confirm that raw outputs do indeed work in pairs. The instantaneous sum of 6 outputs yields a new map, which I refer to as the nuller global throughput map. And located at the center of these maps is an on-axis null, which upon observation, we can see that it undergoes a 90-degree clockwise rotation over the plus minus 4-hour range of hour angle. What you also see in the maps are replicas of the on-axis null, which are also referred to as transmission holes. And these transmission holes would hide the signal of a planetary companion if it was located in one of these regions. But Earth's rotation eventually results in a more uniform coverage of the throughput map, as shown here in the green block. On this slide, panel A on this slide reproduces the throughput map at zenith over an extended plus minus 30 milliarc second field of view. And here we can see that the periodic nature of a nuller, because the transmission holes repeat every 15 milliarc seconds. But as the observation window progressively increases, we see that these transmission holes begin to fill in, with the nuller exhibiting a more homogeneous throughput after an 8-hour observation period, as shown here in panel E. In panel E. Now, Earth rotation does change things somewhat for a favorable target like HIP 107773. So Earth rotation does change things quite a bit for a suitable target like this, but less favorable targets at higher declination angles will still retain some transmission holes in these throughput maps. So therefore, one can use these transmission maps to predict the probability of exoplanet detection at the expected location of the companion. So we now need to, I suppose, look for some planets to discover with this Nulling interferometer. So so for this, to show the astrophysical potential of a kernel nuller at the VLTI, I devised the kernel nuller observing program, discover observing program, and for this I used the proper motion anomaly catalog, which is based on the changes of stellar proper motions between the Hipparcos and Gaia EDR3 catalogs. So I applied various filters to this catalog: the declination of the target, the distance, the mass of the star, and the mass of the planet. And after this, after applying these filters, I then used the Banyan algorithm to determine the probability of these targets, the probability that they belong to a young stellar association, and after determining the age, I then used this species toolkit to determine the photometric properties of the planet as a function of age. Yeah, after doing all of this, I identified 38 companion candidates, which are plotted here in this plot of angular separation versus contrast. The size of the markers in this plot depicts the mass of the planetary companion, which is in a mass range of 1 to 13 Jupiter masses, and based on the limiting magnitude of the VLTI auxiliary telescopes, I can confirm that these planets are bright enough to be detected with medium and large AT configurations. So just a quick recap, kernel nulling provides of what we just seen now. It provides efficiency of nulling and self-calibration, better diversity in signal, and improved characterization. So identified 38 targets for discovery observing program, and all this that I discussed is covered in this publication. So yeah, now some lab work. I performed this lab work in terms of the characterization of a kernel nuller at the kernel nuller photonic chip. This was the laboratory setup that I used in Nice. The key points here are just that the light is injected into the bench, the light source being a supercontinuum laser. The light then travels onto a deformable mirror, which is here. This deformable mirror is used for injection optimization, but also co-phasing of the input beams into the photonic chip, which is located here. Here you see it mounted on. Yeah, it's mounted on the bench. Okay. Yeah, and then also we have a CRED1 320 by 256 fast readout CRED1 camera, and the outputs. So the main work that I was trying to do here on the kernel test bench was to perform the spectral characterization of the chip, and also to demonstrate this self-calibration that I've been talking about previously. And to enable the spectral characterization, I designed a spectrograph which enables this. So yeah, this is the spectrograph. Key things here is that it operates in a wavelength range of 1.2 to 1.75 microns with a spectral resolution of 9.5 nanometers. This is the photonic chip which we used. Key things here, both images are of the same chip. The only difference is that the first one is just meant to show you the waveguide circuitry of the chip. On top of those waveguides are these gold electrodes, and these enable active on-chip phase control. Which won't talk about today. But the key thing as well is that it contains 12 distinct kernel nulling arrangements, and we had different kernel nullers because first of all we were using this photonic technology for the first time, so we wanted to look at different architectures to see what would be the optimal one for the future. So the kernel nuller that I characterized was located in that region on the chip. This is the beam propagation simulation of the photonic device which I used. It's called a multimode interference coupler. Here you see light injected into the input waveguides, and then on-axis light is directed into your bright output, and then you've got these your 3 node outputs. Key parameters of the MMI are the length and width of the multimode cavity and the distance between the input waveguides. And these are the parameters for the multimode interference coupler that I used. And usually in the design process of these devices, these are the main parameters you play around with in order to get this so-called self-imaging effect that the multimode interference couplers operate by. So this is the schematic representation of this 4x4 multimode interference coupler. One of the key things why we tested this one in particular is that we can be able to test brace wall nulling and kernel nulling at the same time. So here you see a brace wall null where 2 out of the 4 inputs are pi phase shifted, similar as before. And here you see the input phases in quadrature, and both are mirror images of each other, and we use these 2 outputs to produce one kernel null, self-calibrating kernel null. It is important to note that this architecture is very similar to the double brace wall architecture, which I haven't spoken about before, but it's also one you would classify as an advanced nulling architecture. The double brace wall was implemented on was chosen as a nulling architecture for the NASA TPF and Darwin missions I mentioned before. But these 2 outputs are analogous, are similar to the double brace wall. The only exception is that a double brace wall has 2 bright outputs. For any nulling interferometer, we can summarize the input phase offsets and beam combinations that it performs with a matrix like this. So this is the ideal matrix for this 4 input, 4 output kernel nuller. So the experimental work was to try to determine how we can build up this matrix by measuring various parameters. Now I won't go into the details of how I did this, but the key thing is that we can experimentally determine this matrix by measuring the beam splitting ratios and the relative phase of the input electric field. And what you measure are 16 distinct complex coefficients that can be split into an amplitude term and a phase term. So you make these measurements and build up this matrix again, and because you're doing the spectral characterization. I did this for 17 spectral channels over the, I think it's, yeah, 1.6 to 1.7 micron range. I think maybe I'll check again. So when you have those experimental matrices, you can then go back and rebuild these complex matrix plots. So here you see what the theoretical complex matrix plot looks like for that 4x4 MMI. And the device was designed to operate at 1.55 microns. Now, you know, it wasn't optimized. You can see it's not perfect. There's amplitude mismatch, phase mismatch, and things actually even get much worse at the edges of the wavelength range. So here at 1.4 and up to 1.6 microns, you can see that the performance is not what you would expect theoretically. But that was not the key point of this experimental work. The key thing was to try to devise a method of how you can characterize these devices, which we were able to do with the method I employed. But also, MMIs are only beginning to be used in astronomical instrumentation. And the material that we also use is not optimized for the wavelength range that we were planning to operate in. But it allows for rapid prototyping of these devices, and you can test so many different features. So, you know, when cost is a trade-off and other things, so this is what we implemented. But anyway, determining this behavior is useful for the future because it would enable us to achromatize future kernel designs, because we know how it performs in this wavelength range. So I suppose, you know, with characterization, it is quite important if one wants to avoid these pitfalls. So anyway, self-calibration. To demonstrate the self-calibration, if you recall, at the beginning I had showed you now depth distributions which look like this. Using the deformable mirror, I injected light into the photonic chip, measured the flux at the outputs, and recorded the null depth. You can forget about output 1 for now, because that's the brace for now. But the two we're interested in are output 2 and 3, which allow us to form a self-calibrating observable. So here I applied phase perturbations using the upstream deformable mirror, and the linear combination of these two outputs gives us this kernel null distribution, which you can see it's much easier to deduce what the null depth would be from a distribution like this. And a further validation of the characterization was that the experimental Nulling matrix that I obtained, I was able to perform a Monte Carlo simulation, which in the same conditions, and you can see that there's a good agreement between the simulation and the experimental data. So this, I suppose, yes, validates what the method was for creating the experimental complex matrix. So quick recap, investigate the spectral behavior of the kernel null in the 1.4 to 1.6 micron range, verified self-calibration with a 4x4 kernel null, and these this experimental work I've discussed today is in this publication. Now to the future. I'm working on the NOT instrument, which is going to be the first Nulling interferometer on the VLTI, and this is being built here at the Institute of Astronomy. NOT uses a double bracewell architecture. So this is some slight similarities to the 4x4 canal I showed you earlier. So some of the work that I've already begun is to build a spectrograph that will enable us to spectrally characterize the NOT photonic chip, and also creating an observation preparation tool. Now this tool will enable people or the community to be able to use it to plan for observations, and it is something that will be deployed later on in the year on the KU Leuven website. On the right, NOT is part of the ASCAD suite of instruments. The key things here is that the two main science instruments are NOT and Bifrost. And the other subsystems are used for injection optimization and fringe tracking. Finally, one of the proposed missions for the future is the large interferometer for exoplanets. And this is being led by ETH Zurich. Life is building on the heritage of the Darwin and TPF missions, and recently there was actually a study that was done where they compared different nulling architectures, and a 5-input kernel nuller was actually confirmed to provide possibly the highest planetary yield for this space mission. So in the future, especially deploying more than 4 telescopes, most likely, yes, they would have to use a kernel nulling architecture. But the main goal for life would be to measure the spectrum of an Earth-like exoplanet, and perhaps this could be the next big milestone in exoplanetary science after the discovery of 51 Pegasi b. So that's the end of my talk.
Thank you very much for your very interesting talk. Are there any questions?
Hi, Peter. I was wondering what level of contrast did you reach with your setup in NIS with the self-calibrated output, and what were the main limitations?
10 to the minus 3 was what was an out depth we were able to get. Main limitations is that we used the injection into the chip was not well optimized. There was some flux leakage of the inputs into the chip, so this could be one of the reasons why we did not get a very low null depth. One of the other reasons was that the photonic chip didn't have photometric taps, so we could only measure the flux at the outputs, but we could not measure what we were injecting into the chip. So this could be one of the reasons why there was some flux losses, thereby not getting a much lower null depth. Possibly, maybe also the material used to fabricate the photonic chip. Silicon nitride might not be the best option. So yeah, that might be. Yeah.
Any more questions?
So, are there any other science cases being planned with the same instrument? What could be possible with this other than exoplanets?
Like exo-zodiacal emission and things like this that is being planned. I think well, there is a working group for NOT, which who are doing this. I think with Denny knows more about this than me, but this is with people in Arizona at the Large Binocular Telescope. Yeah.
Okay, thanks.
Hey Peter, thanks for this nice talk. In your first project, you showed a figure of your simulations of all these targets that you acquired. Did you observe any of those, or it was just like a catalog?
Yeah.
And in that catalog, you had sort of like it looked like a hard limit of 50 milli-arc seconds, or was it arc seconds? I don't know if you can show the plot maybe. I'm just wondering how that limit came to be. I guess maybe that's just because of the. So here you have separation, 50 milli-arc seconds. It seems like to be where you won't go below this. But what is the physical motivation here?
So the mass of the star was estimated at a separation of 5 AU. So we set boundaries as to where the potential companion would be located. So I suppose this is why there is a limit to. There's a limit in the separation of where we would want to detect the companion.
Okay, and that's because the assumption here is that all the stars you're looking at are solar-like, because I guess if you have different distances, different masses of the stars, you would get different outputs.
The assumption is that all the solar type stars with potentially harboring companions in the 1 to 13 Jupiter mass range. Yeah.
Okay, thanks.
Any other questions? Okay. Give me a minute.
Hi. So you mentioned that you showed the simulation for 8 hours of observations, so one night. Is there benefit to revisiting targets and training multiple nights of observations, or is it ultimately just whether or not your planet is there or not? Like, is there a point to such a thing, or is one night enough for each target?
No. So, yeah, you would never get 8 hours for one target. So, for instance, with this nuller discover observing program, the idea, because first of all, the auxiliary telescopes are relocatable. So what you could do is you can have an observing strategy where you are observing multiple targets in one night. And depending on, and you can then apply the particular array configuration for the specific target based on how the UV coverage looks for that particular target. So then you could, the idea would be to observe multiple targets in one evening, and also, so for instance, like with these throughput maps, because you will know at which hour angle is optimal for particular targets. So you could then be able to predict, okay, for this target, I can observe it for this amount of time, then switch to another target, and then maybe possibly come back when it's at zenith or close to that. Multiple targets, I think, is ideal.
Okay, so if I understood what you said, it sounds like there's almost an iterative process. So the initial observations of a target would inform future configurations for the instrument for that target based on the UV coverage and so on? Or is all this known a priori?
Oh, you know before.
Ah, okay,
Yeah,
cool.
yeah,
Never mind.
you know the UV coverage before.
Okay.
Yeah.
Thanks.
Any more questions? Okay, in that case, we can thank Peter again. Thank you all for coming, and see you next week.